Are we done now?
Yes, we are done. He has almost everything that's his.
I wasn't too worried.
He has everything that he needs for this class.
That's all that matters. I don't care about that. Okay, so what we're gonna do is we came up with those equations yesterday, and today we're gonna kind of work through and show you how you can actually use them and kind of look at some deeper truths and kind of play the what if game. So, you got a satellite, 122 kilometers above the surface of the Earth. We want to find how fast it's going, how long it's going to take, the centripetal acceleration and the gravitational acceleration at that point. And we have one number. So, 122 kilometers. So let's talk about the velocity. So this is a plug and chug to a certain extent of fair. So, how are you going to calculate the velocity of that orbiting satellite? Left leg. Give me a second. V equals what?
dv equals the square root of gravity of the Earth times mass over radius.
How about the universal gravitational constant?
Whatever that is.
Gravity is just...
Oh, I don't know. Yeah. Okay.
Perkins, we just call it Big G.
How about the universal gravitational constant?
I like Big G.
I like Big G.
Okay, fine, whatever.
Can we call you Big G?
Yeah, Big G.
You can.
Hey, no problem,
Okay,
Big
you
G.
can call me a lot of things. Just don't call me late for breakfast. Okay. That's an Australian thing. It's like, yeah, you call me anything you want, just don't call me late for breakfast, Nate. Okay. So what are you doing now? You've been my students long enough, and you know human nature. What are you going to do wrong in this problem?
You're gonna say, oh, the R is 122.
No,
We're gonna
forget the
convert to
Add
meters.
kilometers to the radius.
Well, first off, what's the simplest thing you're going to do wrong?
Not convert to meters.
You're going to see a radius, and you're going to put 122 down there. Okay,
Wrong.
Idiots.
and you're going to get a velocity approaching the speed of light. Okay,
Pretty quick.
that's pretty quick. Probably not going to happen. So, first off, what are you going to have to do with 122
Multiply by
kilometers?
1,000.
Did you say divide by 1,000?
I said
He said multiply.
He said multiply. I'm going to stand by my friend here, Burkamp. You said it.
We're all standing.
Yeah, Big G. He said multiply.
See, I got my
What
team
is
on my back.
multiply?
You got your posse.
I'm buzzed in.
You got
What
your
is
conversion
multiply?
posse.
The conversion velocity.
1,000 meters, right? So then you're going to go, oh, there's my radius, 122,000 meters, and that's what you're going to put in for the radius.
Burkamp, what are you doing?
Because the 122,000 just gets you to here, right?
Yep.
Where does it have to be measured from? Center. There you go. Because we treat it as, both of these as a point mass.
I don't have one.
Now, is this mass the mass of the satellite? No. Why am I never going to give you the mass of the satellite?
Because it doesn't matter.
Right, it can't
Don't
be
matter.
okay? So if I double the mass of the satellite, what does that do to the velocity?
Nothing.
Absolutely nothing. Okay? Absolutely nothing. So somebody take 122,000 and add that to the radius of the Earth.
Yeah, I know.
6,049,000.
Scientific.
Ah, well, my calculator don't got that.
You can just
My
say
calculator don't got that.
6.49
Seriously.
times 10.
It don't. The oracle
Okay.
says no.
According to this,
6.49.
6.49 times 10 to the 6th.
6 point what?
49.
49
10 to the 6th.
exactly? Or is there more to
No,
it?
there's like
There's
threes.
three.
Do not round this number.
So
Ever.
3
6.49
Three.
33
And that's exact.
E6.
times 10 to the 6th.
times 10 to the 6th meters. Okay?
Nope.
Plus 5.
Okay? So don't round this number. Okay? When you're adding that, round when you get to the end. but don't round it down. So from yesterday, satellites in near Earth orbit, what should be the order of magnitude of their velocity? 10 to the what?
Third.
10 to the third. What should the orbital period be in seconds? 10 to the third. They're both going to be 10 to the third in seconds and in velocity. So, crunch the numbers. What do you get? And make sure that you can do this calculation. Don't sit back and go, oh yeah, I can do that on my calculator. I'm begging of you, make sure that you've got these numbers entered right. Because if you're not, then you're going to try and do this assignment and it's just going to turn into a
Can I have
train
my
wreck.
calculator back?
So I'm begging you, try the numbers.
Yeah, there you go. There you go.
What'd you get?
7.84. This is we round down.
Okay, yep. Times 10 to the third.
Yeah.
Okay. Now, out of curiosity, this is just kind of a comparison. Speed of sound is about 330 meters per second. So take that answer and divide it by 330.
23.
23.7.
So about 24. So what this means is that this satellite is going Mach 24. It's going 24 times the speed of sound, right? Which is pretty fast. Speed of sound is 330, 10 to the second. You're going 24 times the speed of sound. Now, to give you some perspective, okay? Next thing I want you to do, I want you to take this number, and I want you to divide it by the speed of light, which is 3 times 10 to the 8th. Okay? You don't have to do this. I'm just showing you this as a comparison. So take this, divide it by the speed of light, 3 times 10 to the 8th, and then multiply that answer by 100 so we have it as a percentage. What'd you get?
0.00261.
0.0026. Okay? So even though you're going 24 times the speed of sound, that's 0.0026% of the speed of light.
That makes sense.
Huh?
That makes sense.
That what?
That makes sense.
Okay. All right.
Yeah.
Yeah, so it seems like you're incredibly fast, but relative to the speed of light, you're not. So that's what I'm telling you. If you ever get a velocity approaching, you get 10 to the 6th, 10 to the 7th, something has gone horribly, 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 horribly wrong. Okay? You're not going to get things going that fast. It is not going to happen. Okay? So be very, very cautious if you get any velocities greater than 10 to the 3rd. Odds are something went wrong. Okay. So we got that one done. No worries. So then, let's tackle the orbital period of the satellite. So what are you going to start with to find the orbital period of the satellite? So now, you have to realize, what do you have on your equation sheet? Yeah, what you have is this Swiss Army knife equation. 4 pi squared r cubed equals big G mass of the Earth times t squared. Right? This is what you have to realize. This is what you have to start with. Okay? And you've got to be able to solve this equation for any of these variables. So, McGriddle, what am I going to do to get t by itself?
Divide by the big G in mass.
Okay? Then what?
Square root of.
Yeah, and then take the square root of all of that. So here's what you've got. You've got the square root of 4 pi squared r cubed over big G mass of the Earth. Now, if you were doing this calculation a lot, okay, and if you think about it, this makes sense. This whole thing, this 4 pi squared big G mass of the Earth, this whole thing is actually just one constant, okay? But in this calculation, as long as you're orbiting the Earth, these numbers will never change. You're not going to change big G, the gravitational constant. You're not going to change the mass of the Earth, okay? You're not going to change 4 pi squared. So you could write this, you could, if you wanted to, you could get this number by itself, which is going to be some constant times the square root of r cubed. Okay, so if you were doing this a lot, it would just save you crunching these numbers every time. You can just have this stored out here as a constant, and then the only thing that's going to change is that radius, because that's the only variable that you're going to have. So, but if you look at it, what that means is that period is proportional to what?
Radius.
The square root of r cubed. So as your radius gets bigger, period's going to get longer. So, cross the numbers, what do you get? And we're using that same radius of 6.4933
times 10 to the 6.
Now, here's what you're going to forget to do, is that you're going to forget to cube that number. And if you forget to cube that number, you're going to get an answer less than a second. And so what that means is that you're going to tell me this satellite is going to go all the way around the Earth in less than a second. Probably not going to happen. Okay? So I beg of you, whenever you get some of these answers, look at them and go, wow, does this answer make sense? Okay? So what'd you get?
5.21 times 10 to the third.
What'd you get?
5.21 times 10 to the third.
5,210 seconds. Okay? Now, Mary, divide that by 60 so we get that in minutes.
86.8.
So about 87 minutes, okay? Roughly about an hour and a half, all right? So, and that's like kind of what the International Space Station is at. So it's kind of, it really throws off like called your circadian rhythm, because when you're up there, instead of having like seeing a sunrise every like 24 hours, now you're seeing a sunrise every hour and a half. And so it's tough to get into like a sleep cycle because, oh, hour and a half later, there's another sunrise. Oh, there's a sunset. There's a sunrise. There's a sunset. So you have these going all the time, and so it's tough to maintain a normal body rhythm. Okay, so got those pretty much plug and chug, right? 10 to the third on your velocity, 10 to the third on the seconds. Hey, we're cool. We're off to the races. Now, next one. The centripetal acceleration. Now, how do you know that this satellite is even undergoing centripetal acceleration?
It's not flying off.
In the circle.
Yeah, it's moving in a circle. Now, listen to me very carefully about what I'm going to ask. Is it possible for this satellite to orbit the Earth with a constant velocity?
No.
No.
No,
No. Why, Madeline?
because it's going inward, it's being pulled inward,
So what's changing?
the direction.
The direction of the vector, right? So I cannot orbit with a constant velocity. Can I orbit with a constant speed?
Yes.
Yes, because the speed is just magnitude, right? So as long as this thing is traveling in a circular orbit of what we had last time of that, whatever we get, 7,840 meters per second, okay? So I can orbit with a constant speed, but I can't orbit with a constant velocity because I'm always changing the direction of that vector quantity. Look for that on a question near you on a test on Thursday. Okay, so what are the two ways that I can calculate centripetal acceleration?
V squared over
I could use v squared over r, or I could use
4 pi r over t squared.
4 pi squared r over, yeah, it's kind of important, over t squared. Which one do you want to use?
4 pi squared.
Pretty, which one do you want to use? V squared over r or 4 pi squared r over t squared?
V squared over R.
Okay. So, the velocity was, what was the velocity? 7810?
Yes.
Yeah.
Yeah.
Now, before you touch a calculator, don't touch a calculator.
7,840.
Was it 40?
Yeah.
Okay. And then we've got a radius, 7,840, and then we've got a radius of, what was it, 6 point? What was the radius?
6.4933
4933.
times 10 to the 6.
Now, this is 10 to the third, right? And we're squared. So 10 to the third squared gets me 10 to the 6 divided by 10 to the 6 gets me 10 to the 0, right? So anything raised to the 0 power is basically 1. So what that tells me is this answer should not be a very big number. Okay? It shouldn't be a very big number. If I do get a really, really big number, I've done something wrong. If I get a really, 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 really small number, I've done something wrong. So this is why you want to get in this habit, especially on this unit, of looking at just the order of magnitude. Just saying, okay, hey, ballpark, what have we got going here? Okay, so what do you get?
9.47,
9.47.
or if you use the unrounded, 9.46. Like I used 7836.9.
Okay, but around 9.47.
Yeah.
Okay. Meters per second squared. Okay? So what that means is if you were this satellite in orbit around the Earth, you would actually feel a little bit lighter than you do right now. Okay? Because right now you're used to feeling 1 g, 9.8 meters per second squared. Okay? So you would actually feel just a little bit lighter than you do right now. Okay, that's cool. Now, here's the last thing that we need to find, is that we need to find g at this altitude. So here's the visual that you need. Imagine that I go to the Earth and I build a platform that's 122 kilometers tall. And I'm standing up here on this platform, which is well outside of our atmosphere, so I'm going to be in a spacesuit, but it would be cool. So I'm going to be out here on this platform, and I'm going to drop a golf ball, and I'm going to let it fall, okay? So what I'm trying to figure out is what's going to be the acceleration of that golf ball, or whatever it is, when I drop it. Now, before you even touch a calculator, okay? I'm 122 kilometers above the surface of the Earth, which is about 60 miles, roughly, okay? I'm 60 miles above the surface of the Earth. I'm going to drop a golf ball. Is my acceleration at that altitude going to be bigger or smaller than 9.8 meters per second squared?
Smaller,
Smaller. Why?
because the distance is larger.
Yeah, I get 9.8 if I'm on the surface of the Earth, okay? I'm not at the surface of the Earth. I'm 122 kilometers above the surface of the Earth. So I know when I get this answer, my answer better be less than 9.8 meters per second squared. So, the only way that you can calculate little g, as opposed to big G, is big G mass of the Earth over r squared. Okay? This is why this equation is so important. This is not the mass of what's dropped. Okay? This is the mass of the gravitational source, which is why your gravitational acceleration is not dependent upon the mass of what you drop. It's only dependent upon the mass that you're falling towards. Okay? It's one of the most important things. This is why Galileo got the results that he did. This is why I never give you the mass of what's falling, because it doesn't matter. Yes, the only thing that determines this little g is the mass of what you're falling towards, the moon, Saturn, Jupiter, whatever it is, and how far away you are from it.
I don't
Right.
know why, but I have like written down that I have little g equals centripetal acceleration. I don't know why.
We'll get there.
Oh, okay.
We'll get there.
I didn't know.
We'll get there. Okay. So in this case, I'm going to take big G, mass of the Earth, and again, this is why you store those numbers. And then that radius was, I think I have that memorized by now.
6.49.
Yeah, 6.49.
4933 times 10 to the 6.
meters, and that's going to get
Squared.
squared. So, run the numbers.
It's 9.46.
Ah, oddly enough, you get the exact same answer. Out of this, you get 9.46 meters per second squared. Huh. Is it a coincidence that it's the exact same answer that we got when we calculated the centripetal acceleration?
Absolutely not.
No. Because what's creating the centripetal acceleration?
Gravity.
Gravity is. So, here's what you've got. Oh. When you look at this, here's the story. The gravitational force is what's creating your centripetal acceleration. So here's the easiest way to look at this. The simplest way to calculate any gravitational force would be like the mass of the satellite times g. Well, that equals mass times your centripetal acceleration, because that's the simplest way to express centripetal force. It's just mass times centripetal acceleration. So again, look what happens. Mass of the satellite drops out. Okay, it's gone. So you got little g equals centripetal acceleration. Now, if you go to what the equation that Bree chose to calculate centripetal acceleration, that was v squared over r. Look, if we solve for velocity, we get the square root of g. Now, where did y'all see that equation before? Landon, what does this mean?
Spinning centripetal.
There was something spinning in a vertical circle, right? And remember, that got the minimum velocity that you needed to complete the loop. Guess what? You were in a state of weightlessness at the top, which is the same as being in orbit. You were in a state of weightlessness. So this is the other way that you can calculate the velocity of an orbiting satellite. But, listen to me. Listen to me. I don't recommend this. There's a reason I did not give you this equation. Okay? There's a reason I did not give you this equation on your equation sheet. It's a cool concept, but here's the problem. You have to use g at whatever that altitude is. Okay? So I can't use, on this situation, like I can't use 9.8 meters per second squared. Because if I'm 122 kilometers above the Earth, g isn't 9.8 meters per second squared. Okay? And the radius isn't the radius of the Earth. Okay? So that's why it's a cool concept, okay? And you can use it to get the velocity, but you have to use g at that particular altitude, and you have to use the actual distance from the center of the Earth out to that point. Now, the only time you can get that minimum velocity to maintain an orbit, if you took 9.8 meters per second squared times the actual radius of the Earth itself, then that would tell you that minimum velocity to maintain an orbit if you were at the surface of the Earth. Okay? But, so it's a cool concept. Do not use this equation on the test. Just understand it. Do not use it. You can use it when we get into like centripetal motion and something being at the top of a loop. That's cool. Don't use it on the planetary motion part of it. Okay? Because you can, but you have to be very, very careful about what it means. Cool with that? Good? Got it? Shut that down.
You not like dogs?
No, I love dogs. I just don't response.
Do you like dogs or cats?
You don't want dogs?
I barely remember to feed myself on those days. Okay? I don't want to be responsible.
That's why cats are
Also,
good.
though, like, you seem like someone who would enjoy companionship.
I got papers to read.
Big G hates dogs.
Do you have a TV?
You watch TV?
Rarely.
I hate TV.
What do you do in your spare time? I'm curious.
I really don't have much.
I mean, you grade a lot, of course, but like, what do you do outside of that?
That's basically nothing. Or work on the farm.
He sleeps.
I forget you live on a farm. I forget you live on a farm.
Okay.
I started it like 5 seconds ago because I thought that we would be done by then, but
Yeah, but Eli just doesn't know how to stop.
You're right.
All right. So here's how the other thing that you can use for these equations for. So if you ask Siri and go, hey, you know, what's the mass of Saturn or what's the mass of the moon? Siri will say, boom, here's what I found, whatever. Okay? But to figure out those values, we had to make indirect observations on the influence that those objects had on the objects that are orbiting around them. So we got a new exoplanet, and not only did we find that, we found a moon that orbits it, and the orbital radius of the moon is 3.68 times 10 to the 6 meters, and it takes 20.5 hours. So I want to find the mass of the planet. So here's what you have to visualize. Right? Notice that this is 3.68 times 10 to the 6 meters. Is that the distance from the surface to that moon, or is that the distance from the center of the planet out to that moon? Yeah, this is a center-to-center distance. Okay? unless I specifically tell you, unless I specifically say, this is the distance above the surface, unless I specifically tell you that, you assume that that is the center to center distance, okay? So unless I tell you, hey, like on that first problem, hey, it was 122 kilometers above the surface, okay? Cool. This isn't. This is that radius. And the other problem is, you don't even know what the radius of the planet itself is. You couldn't add it to it if you tried, because I didn't give you that value. Okay, so I got that. So, I've got an orbital period, I've got a radius, and I'm trying to find the mass of the planet. So what am I going to use?
Pocket knife one?
The Swiss Army knife, right?
Pocket knife.
Sorry, I couldn't think of it.
4 pi squared r cubed equals big G mass times t squared. Now remember, this is the mass of what's at the center of the orbit. It is not the mass of what is orbiting, because that dropped out of this equation. So, I want to get mass by itself, boom, divide by gt squared. So what are you going to do wrong?
Not convert hours into seconds.
Leave hours. And
You're going to leave the hours as hours and not change them into seconds, and it's going to be a train wreck, okay?
Train.
Train wreck. You're probably going to get an answer like bigger than the mass of certainly our sun, probably, okay? To give you some perspective, the mass of our sun is about 10 to the 26th kilograms, okay? So, just kind of some perspective. So, I got 4 pi squared. Do I have to do anything with the radius?
No.
No, it's already in meters and it's already the center to center distance. That's easy, okay? So you got 3.68 times 10 to the 6th meters. But what are you going to forget to do? You're going to forget to cube it, okay? Trust me, you're going to forget to cube it. Then I got G, right? And then I've got 20.5 hours. Now, out of all of this, meters, the hours, big G, what's the only unit of time that exists anywhere in this equation? And where do the seconds come from? Yeah, because in big G, you've got newtons, meters squared over kilograms squared. And those newtons are kilograms meters per second squared. So, since this is the only location that you have seconds at all, this is it. That is the only way you have seconds. That's why you cannot leave this in hours, because you're not going to get these to cancel out. But here's the beauty of it. It says that big G is kilograms meters per second squared, so you got second squared down below. Here you're going to multiply it by second squared. That's going to cancel out the seconds.
Wow.
If you leave it in hours, that's not going to work. Okay? So, 20.5 hours, 1 hour is 3,600 seconds. Now again, if you're going to do this as like a sub deal, keep all of the digits. Don't round that. Keep all of those digits, and then what are you going to forget to do?
Square it.
You're not going to square it. Okay? Even though you're going to write it down, you're not going to square it. So what do you get?
I got
73,800.
5.
10 to the 20.
5 point what?
4, 2,
Times?
10 to the 21st.
Anybody else get that?
Yes.
All in favor? Say aye. Aye.
Working on a bird.
Anyone opposed?
Give me a little.
So is G just always going to be the same even if there's different planets?
Yeah,
Okay.
this is why we call it a universal gravitational constant. Because if it changed, I would have to give you that value.
What are we using here?
4.42, 10 to the 21st.
Got it. It's right on the money.
Good job, Felix.
On the money? We're good, Felix?
So Mr. Burkham,
Yes?
is
Great.
that constant? Can we just put that in our calculator as well, or that won't have to change, right? The K, the 5.91 times 10 to the 11, right? Or does,
But
or-
this isn't the Earth, man.
Oh, this, whoopsies.
There's a
Okay,
planet here.
Never mind. I'm sorry. We're on this.
Yeah, we're not around the Earth.
I got excited. That was just.
Okay, if we were the Earth, why would I ask you to find the mass?
You're right.
I mean,
Nicholas.
Matthew?
I'm just saying, you know?
Yeah, I know.
Now, to give you, if you actually live on this planet, it would be pretty cool in some regards. Because what's the orbital period of our moon,
Like 30,
roughly?
like 30 days or something.
20.
It's 28.
Yeah, about 28 days, okay, roughly, okay? So, you go through a phase of the moon, you know, we just went and had full moon last week, okay? And so 28 days later, we're gonna have another full moon. So this planet's this moon's cool, because instead of taking 28 days to orbit, it would orbit every 20 and a half hours. Okay, so this thing would be like hauling the mail going around because of the fact that it's going to be orbiting so close to that planet. Okay, so we got this. We're good? So, and again, this is the classic situation of where you take data and you make observations, like for example, when we found the mass of Jupiter, there's 4 Galilean moons of Jupiter, Io, Europa, Callisto, and Ganymede. And that's how we figured out the mass of Jupiter, is that we kept track of the orbital period of those planets as they were going around, and we knew the radius, and then we worked backwards and we found the mass of Jupiter. Okay? Same thing with the moons of Saturn. Okay? Same thing with Phobos and the mass of the moon of Mars. So if you can figure out what's happening with a moon, then you can work backwards and figure out the mass of the planet itself. Promise you, on the test, you're going to have something like this. I promise you. Okay. One last one, and we're done. Here we go. Here we go. So now we've actually landed on the moon. Okay? We're landed on the moon. And we've set up our little pendulum, and we have discovered that the gravitational acceleration on this moon is a paltry 1.22 meters per second squared. Much less than the gravitational acceleration on Earth. I could probably even dunk a basketball on this moon. Okay?
Yeah.
You do that on
Big
Earth,
G.
Bird camp. Come on.
Used to be able to.
Back in the day.
Haven't since before you were
On
born.
an 8-foot goal.
Huh?
On an 8-foot goal.
His arms reach 9 feet in the air.
So, what does that 1.22 represent?
Little G.
Little g.
Yeah.
Okay, so I've got little g, right? And we've got the radius, 1.40 times 10 to the 5th meters, so we've got this. So I want to figure out the mass of the moon. So what's going to relate that gravitational acceleration, radius, and mass?
Hold on now.
Hold on. Hold on now. Whoa, Nelly.
Yeah, G equals G mass of the Earth over R squared.
Now, are we going to use the mass of the Earth?
No.
No, because this is just the mass of whatever is at the center, right? Okay? That's all this is. This is what we don't know, but this is how we figured out the mass of the Earth, was a similar type deal. So, we know what G is, 1.22 meters per second squared. We've got that. We know the universal gravitational constant, and we know the radius. So the only thing we don't know is the mass. So Olivia, how am I going to get mass by itself?
You multiply by R squared and then divide by G.
Beautiful. So my mass is going to be G squared over big G. So I got 1.22 meters per second squared times the radius of 1.40 times 10 to the 5th meters squared, and then divide that by big G. Don't forget to square that radius. So what do you get?
Oh, I use 1.44. Yeah, that's what I would.
3.59 times 10 to the 20th.
Everybody cool? Al, we're good? Okay.
Eric, do you have your calculator?
Now, to give you some perspective, like our moon has a mass of like 7.35 times 10 to the 22nd. Okay, so this moon would be a little bit smaller than ours. All right. Okay. So we got that one done. Now, the next one becomes a little bit more difficult. Conceptually, it's a little bit more difficult. So, with the next one, I want to know how far I'm going to go from the center of the moon so that if I have a 1 kilogram mass, it weighs exactly 1 newton. Okay? So here's what I want you to think through. If you're standing here on the surface of the moon and you're holding a 1 kilogram mass actually on the surface of the moon, what's that 1 kilogram mass going to weigh?
1.22.
Why? Why is it going to weigh 1.22 newtons? Yeah, acceleration due to gravity is 1.22. You multiply that by 1 kilogram, you get 1.22 newtons. So standing right there, a 1 kilogram mass is going to weigh 1.22 newtons. So here's what I want to know. Is that how far from the center of the moon do I have to go so that instead of weighing 1.22 newtons, it's going to weigh 1 newton? Now, basically, what am I asking you to find? If something's going to weigh 1 newton, what is little g if a 1 kilogram mass weighs 1 newton?
1.
1, right? That's fundamentally it, right? So when a 1 kilogram mass weighs 1 newton, that means that gravitational acceleration is 1 meter per second squared, right? So it's just kind of a magic code for, wow, Burkamp, why didn't you just say g equals 1 meter per second squared? Because that's fundamentally what we're saying, right? So I got little g equaling big G mass over r squared. Now at this point, what do I know?
G is equal to 1. And then you know your gravitational constant and the mass of the moon.
Yeah. Now here's where you're going to screw this up. Okay. Here's where you're going to screw this up. Is this going to be the mass of the moon, or is it going to be 1 kilogram?
Mass of the moon.
Yes. Do not substitute in here this 1 kilogram mass. That isn't the issue. Okay. This is not 1 kilogram. This is the mass of the planet. Okay. That's the whole key to this. Do not substitute in 1 kilogram. So I want to know the center, so I'm going to go, oh, okay, r squared. That's kind of cool. So I'm going to go r equals, I'm going to get r by itself. So what am I going to do?
You're going to divide gm by g and take the square root of it.
I'm going to take the square root of that. Right?
Yes.
Now, what does my answer have to be bigger than?
1.2.
What does my answer have to be bigger than?
1.4 times.
It has to be bigger than 1.4 times 10 to the fifth. Because with the radius of 1.4 times 10 to the fifth, I get an acceleration of 1.22. So it's got to be further out. So I know when I get that answer, it has to be bigger than that radius. You think it's going to be a lot bigger? No, because I'm only dropping it from 1.22 down to 1. Okay, so it's not going to be a lot bigger, but it's probably going to be bigger. So you got big G, you got, what was the mass of, what do we get for the mass? 3.59 times 10 to the 20th. Oh, wrong way. So I've got big G, what was it? 3.59 times 10 to the 20th. Okay, so that's that mass from the last problem, 3.59 times 10 to the 20th. And then I'm going to divide that by 1 meter per second squared. So what do you get?
1.55 times 10 to the 5th.
1.55 times 10 to the 5th meters. Now, Does that seem like kind of a reasonable answer? Yeah. Okay, 1.55 times 10 to the fifth. All right. We're a little bit above the surface of the Earth. G is going to drop from 1.22 down to 1. Okay? Cool. Got it? All right. Now, here's where we're at in terms of what we know about science at this point. So from a historical perspective, Kepler came out and he says, hey, here's my 3 laws of motion. Moving ellipses, they go faster when they're closer, slower when they're further away. Came up with his laws of harmony, which is that Kepler's third law, period of A squared over period of B squared, radius of A, radius of B squared. And they worked beautifully, okay? And then that was early 1600s. Isaac Newton comes along, mid to late 1600s, which is with his work of Principia, says, okay, hey, here's these 3 laws of motion. He comes up with his law of gravity, F equals big G, M1, M2 over D squared. They kind of merge them. They go, oh, right, there's a force acting on planets because they travel in circles. That isn't their natural path. And physicists were feeling pretty good about themselves. Okay, so that was like the late 1600s. But they had one annoying thought because they really couldn't understand or explain what gravity actually is. Okay, and again, we talked about this. You can make the argument that gravity is magic because when I drop something, there's no observable force, but yet it falls. And that's kind of the definition of magic. Because if I put my hand here and then all of a sudden my pop can decided to move towards my hand, you all would go, sorcerer, okay, witchcraft, magic. But if I drop this and it falls, you all go, oh, okay, well that's just gravity. Okay, even though there's nothing, there's no interaction whatsoever. You don't see anything. You don't feel, it's like, oh, I feel gravity in the room. It isn't like it's humid. You know, it's like, so you walk, it's like, oh, gravity feels so thick today. Oh, you know? So that was late 1600s. So for about 300 years, we really didn't have a new explanation of what gravity was. We knew its effect, and so Albert Einstein comes along and says, "Hey, let me take a shot at this." So, Mad Max, stop that, and let's go to.
Hey, can you give me that? The camera needs to be stable.
What are you timing?
Got him.
Okay.
I didn't do it.
I know. I'll vouch for you.
Thank you.
Nice. Okay. So this is like spandex, okay? Which is just should be outlawed for most people, but that's just
Too bad you weren't in pink spandex.
not gonna happen.
If
Well,
you
it
suddenly
will,
get
but there's a lot of money involved. Okay. Huh?
If you start a YouTube channel teaching science in pink spandex, YouTube will
Everyone
make
would
so
watch.
much.
I did it for
okay,
No one would want to see that.
At least
Okay.
a million subscribers.
No way.
People
No
would watch that because
way.
they think it's funny.
Most
No
of
way.
it, yes.
No.
It wouldn't have anything to do
No.
with science. People
My
watching YouTube make fun of.
pride would not allow me to do that.
can I do it?
Okay.
I don't have pride.
And you don't want to see it either. So let's be honest. And my brother would have to kill me. No. My brother and I have a certain blood pact. If we ever see each other in spandex, rollerblading, or owning a minivan, the other one has to shoot them.
Hey, that doesn't mean you have to be killed.
Yeah, exactly. You got true.
That does not.
If your older brother, then there's no way. It's hilarious.
That does not mean he has to kill you. He just has to shoot you.
No, the point being.
Okay.
Yeah, like center.
What is Bird with a hole or something?
Okay.
Sunken?
So, you can actually show a lot of Newton's laws with this contraption. So if I take this marble and I just roll it across,
Whoa.
for the most part, what's the path of marble?
Straight.
Pretty straight, right? Okay? I'm not going to be able, if I roll it across like that, it's going to go pretty straight. Why?
There's
No other
nothing.
forces acting
Yeah,
on it.
and there's no forces acting on it to change the direction. Am I changing the magnitude of the vector?
Yeah.
Yeah.
Yeah, because there's some friction, right? So if this was like a pure frictionless surface, it would just go back and forth the entire time. So Einstein says, okay, let's look at space and time as a fabric, okay? Because everybody kind of viewed time as a separate entity from space. And Einstein says, hey, let's just kind of weave them together. So he kind of said, all right, I'm going to take this mass, I'm going to put this in the middle. So that's like taking the sun and putting that in the middle of our solar system. Now, when I try and roll this by, instead of traveling in a straight line, it travels in
Curved path.
a curved path. So what Einstein says is that when the Earth is circling in its orbit around the sun, there is the centripetal force, but it's also riding a ridge in the space-time continuum. So it has to follow that particular ridge based upon a certain set of conditions of velocity and distance. Now, here's how you can also show Newton's third law. Because everybody focuses on the small marble. But if you notice, when it goes by, if you notice on that big marble, when it goes by, you'll notice that that bigger marble moves just a little bit. Okay? And that's Newton's third law. It says for every force there is an equal and opposite force. So when that thing goes by, why does that bigger marble move just a tiny bit?
The gravity from the smaller marble.
Yeah, because that smaller marble is creating a disturbance in space and time. So the other one has to respond to it. It doesn't move as much. Why?
Has a larger mass.
It has a lot more mass to it, right? But it's still going to create that force. So when you have a satellite orbiting around the Earth, and everybody says, oh, the satellite is being pulled in towards the Earth, and it is. But guess what? What's that satellite doing?
Pulling in
Over
there.
the Earth.
Yeah, same thing is true of the moon, which is why we have tides, okay? If the moon wasn't pulling back on the Earth with an equal and opposite force, we'd never have tides.
Why?
But
Sorry.
because if the force just went one way, if the force was only being exerted on the moon, and the moon wasn't pulling back on the Earth, then that water would never shift. But because the moon's pulling back on that water, that's why you get the tides, okay? Now, let's say we want to go to the moon. So we're going to let this represent the Earth, and we're going to let the smaller mass represent the moon. Okay? So basically, the bigger the mass, the deeper the gravitational well that it creates. So basically, here's the sequence. You fire the rocket, okay? You get it into orbit around the Earth. You orbit it a couple times. And then you fire the rockets and you get out of the Earth's orbit and you coast towards the moon. You slow it down and it gets caught in this orbit and goes around. And then you go, okay, time to go home. You fire the rockets and boom, we're off and we're home. But here's the deal. This is creating like a gravitational well. The Earth is. That's deeper than the moon's. So if we fire the engines and we're not going fast enough, what's going to happen? It's going to come back. Just like if I take this marble and I throw it up in the air, okay, it comes back down. But if I throw it fast enough, it won't come back down. So when they were orbiting the Earth, when they fired those rockets, they had to be going fast enough so when they shut off the engines and they began to coast, they would be going fast enough to get here. So to give you some perspective on the relative scale on this deal, if this was the Earth, and this was the moon, and you shrunk this down to the size of a football field, okay? So here's the Earth, here's the moon. The moon would be the size of an apple on the 100-yard line, okay? And to get this thing into orbit, you're standing down here and you're going to shoot the apple with a gun that's 100 yards away. You don't want to hit the apple because that way, if you hit the apple, you crash it into the surface and that would be bad. So, but it's the equivalent of just shooting an apple that's 100 yards away and you just have to nick the outside skin of that apple. Okay, you don't want to hit its center mass. You just have to nick it. So imagine the complexity of trying to shoot a bullet at an apple the length of a football field away, and the only thing you want to do is nick the surface. That was the challenge of getting something put into an orbit. Now, what if I just put this marble halfway in between the Earth and the moon? What's it going to do?
Go towards the mass.
Why?
Because of the more gravitational pull.
Okay, in this case it has, in terms of a deeper gravitational well, right? So if we just stop the space shuttle or the lunar command module or anything, and if we just stop it halfway between the Earth and the moon, it's going to begin to accelerate towards that way. Is it being pulled by the moon?
Yeah.
Yes, but which direction is the net force? Towards the Earth. Now, is there a point where this object would be equally pulled between the Earth and between this object and the Moon and this object and the Earth?
Probably.
Closer to the Moon, closer to the Earth. So, but if I get it too close, wait.
What about like the outer layer, like the near the circumference?
What do you mean?
If you put it towards the outer side of it, would it do anything?
Oh, over, like over here?
Yeah, or even like towards you.
No. Well, we'll get to that.
Okay.
Okay, let's not worry about that for now.
Okay.
Okay, so this is one of the things you're going to calculate on today's assignment. It's what's called the Lagrange point. It's named after the French mathematician that came up with this idea. So the Lagrange point represents a single point where if we could stop the spaceship or put any object right here, it would be equally pulled between the Moon and this object and between this object and the Earth. So that object would remain stationary as the Moon was orbiting around the Earth. Okay, this is what's called the first Lagrange point. The second Lagrange point is out here, and there's actually a total of 6 Lagrange points that are centered around it. We're only going to deal with the first 2 because that's the simplest math. So if you're NASA, you kind of need to know when it's going to cross this point. Because when it crosses that point, what's it going to start to do?
Go towards
Orbit.
Yeah, it's going to, more importantly, what's it going to start to do?
Accelerate.
Well, I know that, but what's going to happen to its velocity?
It's going to accelerate.
It's going to accelerate, right? Because then it's going to be going faster and faster and faster. Now, when it crosses that point, is it outside the gravitational field of the Earth?
No.
No. But it's just that net force is now pointing towards the Moon. So here's the problem. If you're going to get caught in the Moon's orbit, you can't be going too fast. Because if you're going too fast, it's just going to slingshot past it. So one of the things they had to do is actually slow that ship way down to get caught in an orbit around the Moon itself. Because otherwise, you had to do that or you just blow right past it. That would be bad. So what happens is they orbit this, okay? Then they fire the engines, boom, they're on a trajectory home. So once they cross this Lagrange point going back, then what's going to happen to the velocity?
It's going to speed up.
Then it's going to start to speed up. And as you get closer and closer and closer to the Earth, what's going to happen to the rate at which it's going to speed up?
Stronger and stronger.
Yeah, because you're getting closer and closer and closer, you're getting deeper and deeper into that gravitational well. So that was the challenge of bringing the Apollo spacecrafts home, because they were entering our atmosphere at such incredibly high speeds. They were going roughly about 7 miles per second. Okay, so if you consider something in orbit is about 5 miles per second, these ships were going about 7 miles per second. And so that was a tremendous amount of kinetic energy that you had to dissipate, and that's why you have the heat shield and it would burn up in the atmosphere. Now, when you have binary stars get weird. So let's say that you have a binary star system and you try and put a planet in orbit around a binary star system. Okay? Yeah, I mean it does. That was it.
Whoa.
Whoa! Yeah, hours of entertainment fun. So when you have a binary star system,
There it is.
one point I'm going to get that thing to stop right in the middle. So when you have a binary star system, math becomes incredibly more difficult because instead of just having one curvature of space, now you have 2 of them. And you always have this continuous interaction between a strengthening gravitational field towards one and a weakening gravitational field towards the other. So, oh, that was a good one.
Nice.
Oh, nice.
So it's supposed to stop in the middle, though?
No. I'm just saying, at some point, it would have to be just right to get it to stop in the middle. No, it's not supposed to stop in the middle.
Do it with the big ball.
Well, the problem is nothing. It's pretty boring because
Oh yeah, it's kind of rolls on the ground.
yeah, it just boring. Yeah. So the smaller one's a little bit. So, hold on, we can't finish on that
What
one.
if you had a trinary?
No.
What's that called?
Goodness.
Back off me.
Try now.
What is that word?
Okay. Now, one of the things that we'll talk about, and this is on your equation, it's on the lecture notes, and it's called escape velocity. So escape velocity is how fast something has to be going to leave a gravitational field. So let's just say I go back to one system. So if I roll this thing up the hill, okay, it's going to come back down. But the faster I throw it, guess what?
Longer it takes.
Yeah, the farther it goes. Now, if I throw it fast enough,
Oh, it's gone.
it's gone.
Hit him in the
Okay?
Black hole.
So that, no. No. So that's the escape velocity. That's how fast you have to be going to escape a gravitational well. So if you're trying to leave our solar system, what's the biggest gravitational well that you have to escape?
The sun.
The sun.
The sun, right? Because the sun is creating this huge gravitational well. Now, out here, let's say here's the Earth, right? So that doesn't create as deep a gravitational well. But if you're trying to launch something from the Earth to escape our solar system, not only do you have to overcome our gravitational field, which relative to the sun is pretty weak, but you also have to overcome that gravitational well as well. So, yeah, as
Is
well.
that
as well.
possible? Can we do that? Do we have technology to do that?
Oh, yeah. We
Voyager.
sent probes out of our solar
Yes,
system.
it's
At least, I can think of at least 2 right off the top of my head.
So we're gonna move to another planet one day.
Avatar.
We need to.
I think we'll destroy this one before we get to that point.
We need to.
The problem is, the
Wanna hear
distances are
conspiracy
just so vast that,
That's the only way human race is gonna survive, Berg.
Conspiracy.
well,
theory.
I'm
We once lived on Mars, but we completely
Okay.
destroyed that like we're destroying
Got the
Earth now,
idea.
and that's why it's a barren wasteland.
back we
No,
go.
that's Venus.
What?
Because Venus has a runaway, like, greenhouse
Greenhouse
gas effect.
And the atmosphere would crush you.
But we're just talking about how like we used to live on Mars and we destroyed it and now we live on Earth.
Wait, the atmosphere
Oh,
was
shut
up.
It's a conspiracy theory.
Dumb.
Now, let me kind of get you started on problem number 10. And this is this problem with these Lagrange points. I'm going to show you a couple of different ways that you can solve the problem. But here's the basic setup. Here's the Earth. Here's the Moon.
Yep.
Okay? And we're going to fire the Lunar Command Module. It's going to go towards the Moon once it leaves our orbit. And what I'm going to find out is the first Lagrange point where, when it gets to this point, the gravitational force between the Earth and the Lunar Command Module, imagine this being like a vector representing that force, is going to equal the force towards the Moon. Okay? So I want that single point where these two forces acting on it are the exact same. Okay? Now, I told you the overall distance from the Earth to the Moon is what,
844.
times 10 to the 8th?
Is that radius?
No. Well, that's the orbital radius of the Moon,
Okay.
not the radius of the Moon itself.
Okay.
But that's the distance from the Earth to the Moon. Okay? Now, I also told you the mass of the Moon is what, 7.35 times 10 to the 22nd? You might have to look at the problem up
Yes.
above. 7.35 times 10 to the 22nd?
Yeah.
Kilograms. Okay, so here's what I want to find. I want to find this force first, between the Lunar Command Module and the Earth. Okay? We'll worry about the Moon later. Let's just not even think about the Moon for now. So I need 3 things to find the force between the Lunar Command Module and the Earth. I need 3 things. I need to know how far apart they are.
The mass of the Earth.
The mass of the Earth and the mass of the Lunar Command Module, right? So that force is going to equal big G, the mass of the Earth, the mass of the Lunar Command Module. Now, I don't know what that distance is. I don't know it. So what do you want to let that be?
1.
You don't know what it is. Yeah, you don't, well, you don't know from Earth to the first.
Yeah, I don't know this distance. So what's the easiest thing to let it be? No, you can't let it be 1. X!
Oh.
It's X! X, but what are we going to do with X?
All for it.
Square it.
We're going to square it.
I heard Maddie and shit. I just,
Oh,
Okay. Now, pretend that that number, that whole thing doesn't exist. We'll get back to it.
so you can't do smash mouth through this capacitor?
No, you can't. You can, but it would take you forever to get there. Okay? Now, that has to equal the force going this way. So what three things do I need to find the force acting in this direction?
Mass of the moon.
I need big G, but not the mass of the Earth.
Mass of the moon.
I need the mass of the moon. And all, what else?
And the
Mass of the lunar command.
Mass of the lunar command module. Now, what's here?
Y.
What's the total distance?
total distance is.
Total distance is 3.844 times 10 to the 8th meters, right?
X squared.
So how much is left?
That minus X.
Ah, that minus X.
Oh,
And then all.
Oh, great, you like that?
I like it.
Whoa!
I like it.
So,
Oh my god.
so
What?
that's going to be 3.844 times 10 to the 8th minus X. But
Swear all.
we've got to square it. Okay? Now, great. So you seem to be fairly excited about this problem. What's going to happen to the mass of the lunar command module?
It's gonna cancel out.
Yeah, there's the reason I didn't give you the mass of the lunar command module. You don't need it. What are you going to do with big G?
Cancel it.
We're going to cancel that out. Okay? So that simplifies things a lot, right?
Yep.
So here's what I'm going to do. I'm going to cross multiply. I'm going to take the mass of the Earth times this quantity, and that's going to equal the mass of the moon times x squared. Okay? So I'm going to start that on a new screen, so we're kind of regroup. Mass of the Earth times this, mass of the moon times this. Okay? So I've got the mass of the Earth over x squared equals mass of the moon over 844 minus x quantity squared. Okay, so I'm going to cross multiply. So I've got the mass of the Earth times 3.844 times 10 to the 8th minus x quantity squared. And that's going to equal the mass of the moon times x squared. Now, to simplify this a little bit, so we don't have to deal with such huge numbers, somebody take the mass of the Earth, which you all have stored in your calculators, and divide that by the mass of the moon, which is 7.35 times 10 to the 22nd kilograms. Just take the mass of the Earth divided by the mass of the moon.
Then you square root.
No. Just give me the number.
Okay.
Just give it's 80 or 90, something like that.
81. How many decimal points you want?
Give me two decimal places.
81.35.
81.35. Now this has no units because it's kilograms divided by kilograms, right? And then I got 3.844 times 10 to the 8th minus x squared equals x squared. Now at this point, you can solve this two different ways. I'm going to show you both ways. How you choose to solve it doesn't make any difference to me. Okay? So here's option number one. So let's pretend that you're back in an Algebra 1 class. And if I said, hey, I want you to expand the quantity x minus 3 squared, what would you get? You'd get x squared
Minus 6x
minus 6x
plus 9.
plus 9, right? Because it's negative 3 times negative 3, negative 3 times x, and you double that, you get negative x, right? Old hat. So one option is that you take this and you expand it following that process. Okay? So you would have this number squared this number times x doubled, and then plus x squared on the end. And then you'd have an x squared over here. So then you'd have to distribute the 81.35 over that expansion. And then get everything on one side where one side equal to 0, and then use the quadratic formula, negative b plus or minus b squared, all that good jazz, right?
Quadratic form?
What?
Oh, the x squared?
Yeah.
Okay, yeah.
Negative b plus or minus b squared root of b squared minus 4ac all over 2a. Okay. If you wanted to do it that way, you can. It would be the biggest binomial expansion you'll probably ever do in your entire life. But you can do it. If you want the challenge, you can do it. Now, here's the other thing that you can do. You can just take the square root of everything.
Yep.
I like that.
Okay?
How would you go through the other one? Dude?
No, I'm just
No,
giving,
that was a rhetorical question.
I'm just giving you the options, okay? Don't judge,
No, I
okay?
wasn't judging.
I'm just giving you options.
I would never judge.
So what's the square root of x squared?
Why would we ever do it the other way?
X. The square root of all of this is just going to be 3.844 times 10 to the 8th minus x. But here's the deal. I have to have two possible roots. Even though I'm doing it this way, I have to have two possible solutions. But what's the square root of 81.35?
Plus or minus.
Plus or minus
9.02.
9.02. So here's what you're going to do. This is how you're going to get your two possible roots. Option number one, you take a positive 9.02 and you distribute it over this quantity, okay? And then you get all your x's on one side and you get all the numbers on the other, okay? That's going to get you one root. The other root, you start over and you take negative 9.02 and you distribute that, and then you get all your x's on one side and all the numbers on the other. Okay? So basically it's an algebra 1 problem with really, really big numbers. Okay? But that's how you're going to get your two possible solutions. Distribute a positive 9 and then completely start over, and then distribute a negative 9. Okay? That's how you're going to get your two roots. What you'll see is that one root gets you inside the distance between the Earth and the Moon, and that's what you're calling Lagrange point number 1. The second Lagrange point puts you on the other side of the Moon, okay, which is that second Lagrange point. So that's what you're going to do with the two possible solutions, okay?
So is the bigger number
The bigger number is going to put you outside the Moon's orbit. The smaller number is going to put you inside the Moon's orbit. Now, let me kind of get you started on some of these problems. If you look on problem number 1, you got the gravitational attraction between the cannonball and the marble separated center to center distance by 40 centimeters, 0.84 times 10 to the negative 10 newtons. Compute the mass of the marble. So, is anything in orbit on problem number 1?
No.
No. So on problem number 1, this is what I would suggest. I'd start off and go, oh, nothing's in orbit, so I got big G, mass of the marble, mass of the, what's the other one? Bowling ball, divided by distance squared. Okay? Guess what? You know everything but the mass of the marble. Now, when you get to question number 2, you got two identical spheres separated by a center distance of 1.2 meters, which is about like EA. Okay? Experience mutual gravitational attraction of 1 times 10 to the negative 4th. Compute the mass of each sphere. What is the single most important word, do you think, in problem number 2? Identical. So if you let M1 be X, what does M2 have to be?
X.
X. And when you multiply X times X, you get
X squared.
You don't get 2X, just saying. Now, when you get to question number 3, at what center to center distance from the Earth would a 1 kilogram mass weigh 3 newtons? Okay? So, a 1 kilogram mass right here in this room weighs how much?
9.9.
Why 9.8 newtons?
That's its gravitational acceleration.
Gravitational acceleration right here is 9.8 meters per second squared. So I want to figure out how far I've got to take this 1 kilogram mass so that G drops to what?
3.
Yeah, so basically the code on that problem, I'm asking you, how far do you have to go until G from the Earth's gravitational field drops to 3 meters per second squared? Okay? Yeah, put all these, work these on another sheet of paper, leave plenty of space between the problems, okay? So this will be due on Thursday, so tomorrow we will review and take the test on Thursday.
What would be like a good stopping point? Like,
If you could get through 10 tonight, that'd be pretty solid.
okay.
And that's not a big deal.
Huh?
If you can
What?
get through 10